Really, there's just no two ways about it. If you want to be great at product development, and I know you do, you have to know what's covered in this video. What annoys an oyster most? A noise factor that's messing up the oyster's product performance. That's what annoys an oyster most. Certainly any self-respecting product development oyster anyway. What is a noise factor? Are noise factors making my product not work consistently? What are some categories for them? Are there any strategies to deal with noise factors? And what on earth am I supposed to do about noise factors while running experiments? I'm going to cover all of that by walking through this noise factor primer that you can download for free. The link is in the description below. And if you like this content, please like and subscribe while you're down there. Also, I'm going to be using a competitive archery bow as a product example, just a heads up, because I've been watching the Olympics and wow. So let's start off with control factors versus noise factors in the context of product design and development. Control factors are the design parameters we can adjust in the development of the product that affects how the product performs. For the bow, that's any of the physical dimensions, the pullback force, basically anything that you set in the design of the product. That's control factors. You have control via the design. Noise factors are all the things that impact product performance, but that we don't control. So variation in those factors can result in variation in the product performance. For the bow, for example, wind is a huge one, right? We don't control the wind. We'd like to, but we don't. And that can impact where the arrow goes, where the bow shoots it. Any inconsistencies you've had in how your product performs, those headaches on your project, it's due to noise factors. You can be great at your technical discipline, but you need to learn how to deal with noise factors to be a great product developer. For example, you could flex your technical muscles every which way and design a new bow that can shoot twice as far as any other bow in history ever. And that might be an amazing technical achievement. But if the bow can't consistently shoot that distance, it's not going to be a great product. Let's run through the noise factor categories. There are a few that are internal to the product and a couple that are external. The first internal category is unit to unit. This is the impact of variation from the manufacturing process, any sort of operations, assembly, etc. Even if the product is fully within specs, there's variation. That's why we have specs, to limit how much that particular parameter impacts the performance. But the parameter still impacts the performance to some amount. It still varies some amount, and so we'll have some contributed variation to the performance. Keep in mind, this could be from one product to the next as they're coming off the line, or it could be long-term process drift, right? Overall, the process isn't changing somehow. For a bow, it could be the rigidity of the limbs. Those are the arms that make up the bow, the big longy things. Now, we can have a spec on that, but all of our bows won't be identical, right? There's going to be some variation in those dimensions. The next category is deterioration. Time waits for no product. Also, cycles wait for no product. That part didn't really work nearly as well. But anyway, reliability is a lot about this. Reliability testing is typically measured in either time or cycles, and deterioration is often the cause of those late life failures, the time or the cycles having enough of an impact on the product such that it doesn't perform the same way anymore. Back to the bow limbs, they could deteriorate through their repetitive flexing, right? By work hardening or work softening, depending on the material, right? Every time you pull it back, it flexes, and after a while, something's going to happen to that material. And yes, I totally just hinted at a way to deal with those noise factors, but we'll get to those strategies in a little bit. The last internal category for noise factors is system interaction. This is when one part of your product messes with another part of your product. It could be an intentional output of that first part or unintentional. Either way, it's got a side effect causing variation in something else, again, in your product. On the bow, the main function of letting go of that string is to shoot the arrow, right? But there's a force release of the entire system, and not all of the energy, certainly 100% of it, is transferred to the arrow. Some amount of the energy could cause a jerk of the bow, pushing the arrow off target as the arrow exits the bow. As that example demonstrates, a tool that you can use to manage system interaction of noise factors is to track the mass, energy, and information of the system. Any losses as your product functions in those three things is a potential noise factor. On to external noise factors. In super simple terms, external noise factors are broken into two categories. They're either from the user or not, right? So they're usage-based or environment-based. Environmental noise factors include all the ambient things, the temperature, the humidity, anything weather-related. They include vibrations and electromagnetic interference, and included are other products in the environment, which is often a hidden one product development folks don't always think of. Now, even though I said it was everything not user-related, it still sort of is, because often the users can decide where to use the product, and the product is subject to whatever the where has for an environment, right? They use it outside or inside, for example. Now, I mentioned wind earlier. That's an obvious one. Less obvious might be the thermal expansion of the bow on hot days, although I bet that's plenty obvious to Olympic archers. The last noise category is usage, and this is a pretty huge category. It includes the differences across the users themselves, as well as how they use the product, how they engage with it. It's also the furthest from our control as product developers. And by the way, directions, instructions for use are laughable solutions to that. Users will find every way to use and abuse your product that you could possibly think of, and then they'll find other ways as well. But even if users were delicate with the product, there are still all the different use cases, human factors like anatomy and physiology, user-based configurations, and of course, their behaviors when engaging with the product. The size and strength of an archer, for example, will impact the usage of the bow. So a bow won't perform exactly the same way from archer to the next. Two archers could have different techniques, for example, resulting in variation of bow performance. On top of that, an individual archer may not be perfectly consistent with their technique, even the Olympic ones. A bow that is very robust against usage noise factors would perform the same even when inconsistent archer technique. So, with those categories out of the way, how might we make a product more robust against the noise factors? Well, there are four main strategies: source elimination, path interruption, control system, and robust design. Source elimination is when you identify and remove, or deactivate in some way, the origin of the noise. This strategy is generally more useful for the internal noise factors than the external ones, and it typically includes a redesign of the product or process. Using different materials, for example, is a big part of this strategy. Like using carbon fiber for the bows, so they last longer and stronger, right? They're more robust against deterioration noise factors. The cam designs on bows have advanced a bunch over the years to ensure more consistent transfer of force, so they're more robust against the system interaction example that I mentioned earlier. The next strategy is the path interruption strategy. Now, this is when you create a barrier or isolation to block the noise. And it's a pretty straightforward strategy, to be honest. So for example, the finger tab used to pull the bow string, right, pull it back, it protects the archer's fingers, but it also provides a barrier between finger variations and the string. Fingers are not perfectly shaped, and they have some variation, and that might affect the performance. The next strategy is to create a control system. You develop a system to counteract the impact of the noise. The noise still happens, but the product adjusts for it. Now, it can be an intelligent system, like with computing power and everything, but it can also be really very basic. Like if a bow had a rubber grip, allowing it to conform to different hand sizes. I'm not actually advocating for this. I'm not saying it's a good design idea. Rubber grip would probably introduce even worse noise factors than were already there, but it's an example of a basic control system. The last, but certainly not least, and possibly the most, bestest strategy for managing control factors is robust design. This strategy results in the most elegant solutions, and it's really how you can master noise factors versus just reacting to them. Robust design is when you set control factors using noise and robustness experiments to make the system resistant to the noises. It's a fairly complex approach, but a simplified example might look something like this. You are developing a bow and you learn through experiments that the bowstring is highly subject to temperature. And so then you run some experiments to identify a material and a form factor that make the string more robust against temperature. That is, you make it so the string performs consistently regardless of the temperature. The last thing I'll discuss on the noise factor primer is how to treat noise factors during experimentation. Now, as I've been talking through this whole video, noise factors add variation to a product's performance. Right? All the noise factors examples I gave on the bow would result in imprecision in the arrow hitting the target. Right? The arrows would hit all over the place, maybe even not even hit the target. And the strategies that I went through would help make the bow more precise, getting those arrows to hit the same place over and over again. However, aside from the product performance in the customer's hands, like when they're out in the marketplace using it, noise factors can also make it a pain to get the control factors right as you're actually developing the product before you launch. Now, if we were to say developing the bow and experimenting on how the dimensions of the limbs impacted the strength, any variation in the material of those limbs, which is a part-to-part noise factor, would make those experiments harder. Right? It would drive up the sample size. It would be more difficult to draw conclusions from that data we get because there'd be more variation in that data. The bottom table on the noise factor primer gives some suggestions on how to treat noise factors when you're running experiments. And it's because there can be some leeway there, because sometimes you can control noise factors, or at least measure them, when you're running experiments at your organization. For example, you can't typically dictate at what temperature customers use your product, but you may be able to control the temperature at which you run your experiments, right? At the very least, you could measure it. You can take that into account. That table at the bottom of the primer helps you through that and what you should do with noise factors during your experiments. Time for an awkwardly inserted side note. If you have a software-only product, you may need to adapt some of this thinking to a software-only context, but it's still all valid. Albeit some parts will be more directly applicable than others, but still all valid. In closing, I suggest you download the Noise Factor Primer right now if you haven't. To make a great product, you need to be proactively identifying and addressing noise factors. Thanks.